Hello everyone and welcome to the afternoon session on machine reading and society. My name is Chris Quirk. I'm a researcher here in the Natural Language Processing Group at Microsoft Research Redmond. And I'll be your session chair for this afternoon. This 1.5 hour session will feature 3 speakers presenting on scenarios, techniques, and the broader societal impacts of endowing computers with the ability to read, to extract facts from natural language and convert them into a machine-readable format. And as we shall see, machine reading is poised to transform the way humans work by illuminating and consolidating the world's information. Our first speaker is Oren Etzioni, who leads the Allen Institute for Artificial Intelligence. His career includes both entrepreneurial successes, leading several companies to successful acquisitions, as well as academic honors as a professor of computer science at the University of Washington and AAAI fellow. One of his papers in particular popularized the term machine reading and helped form a community in this important research area. Today he'll be discussing some of his recent research topics at AI2. Welcome, Oren.
Thank you, Chris, for the kind introduction. Hoi Fung for organizing the panel. And also, Chris even gave me his laptop so I can try to do a demo. It's unfamiliar technology, so we'll see what happens. Let me jump right in because time is short. As Chris mentioned, I lead the Allen Institute for AI, which was founded by Paul Allen. He previously founded this other company thing. Anyway, in one of his lesser endeavors, he founded the Allen Institute for AI. We're now 60 people, and as I always like to mention, we're hiring. So please keep that in mind. AI2's research methodology is to focus on grand challenge problems. We try to define ambitious goals and at the same time have measurable milestones. We focus on research tasks and goals rather than on specific mechanism, which makes things interesting for us. And our mission is AI for the common good. We're trying to have high impact on society through AI research and engineering. It was a real pleasure hearing Bill Gates in the other session. He mentioned the huge potential benefits of AI, also talked about the risks as footnotes. I think he presented a pretty balanced discussion. My favorite part, though, when he says, "That's the stupidest thing I've ever heard." I feel like, okay, I can end my career now. I've heard him say that live. Anyway, so what's the societal problem we're trying to solve? It starts with what I like to call Moore's law of scientific publication. Somebody in a recent book pointed out that the number of scientific papers published has doubled every 9 years since World War II. In our own data on computer science, we see this exponential curve. So this is computer science papers in our corpus at Semantic Scholar over the last 40 years. And you see it's almost a perfect fit to an exponential. So that's a problem if you're trying to do academic research, right? There are no Renaissance men and or women anymore. It's impossible. And so let's say I'm trying to get up to speed on deep learning, and I type that into Google Scholar, which is the engine that most people use these days. It very rapidly comes back with more than 3 million results. So more than 10 years ago when Google Scholar started, the fact that it was fast and increasingly comprehensive was it. That's no longer the case. We just have too much information. It's still wonderful to have it as a resource, but we need some way to be more selective, right? To be able to home in on the key results. And that's the focus of our work. It's not just that the number of papers is so large, it's also the number of citations. Each of these papers might have, a popular one might have 500, 1,000, 10,000 citations. Each of those citations will have several hundred citations. The citation closure is easily tens of thousands of papers, at which point you give up and you just cannot do a comprehensive search in a given area. So our idea is that we can leverage AI techniques to combat this kind of information overload. And yeah, we introduced the term machine reading back in 2006 and tried to galvanize interest in using the techniques that people have been working on for a long time, information extraction, et cetera, to try and do something more ambitious. And two noteworthy things about this concept as we defined it about a decade ago is one, that we're trying to do it with a minimal amount of labeled data. We all know the phenomenal success of deep learning techniques when you have a large amount of labeled data. When you don't have a lot of labeled data, which is often the case when you're trying to analyze scientific publications, right? You can't just hand them off to Mechanical Turk and have people label the data. Life becomes a lot more difficult. And likewise, when you're trying to analyze arbitrary topics. Let's say you have 100 million PDF files across a wide range of sciences, and you want to figure out little things like, what are the papers saying? Well, you need to have very scalable techniques to do that. So, so where does that lead us? It leads us to an engine which I'll demo for you shortly called Semantic Scholar. It's as part of, it's a nonprofit. It's not a product that we're trying to monetize. AI2, the Allen Institute, is a nonprofit institute, and we're just trying to build a better, more selective engine to cut through the clutter. Semantic Scholar is currently only focused on computer science papers, but we're rapidly expanding it. We're going to launch in neuroscience later this year and move to additional scientific areas. I'm curious, how many people have heard of Semantic Scholar before today? Oh, made my day. And how many people have actually used it? Okay, good, good. And how many people are using it regularly? Okay. Our statistics, thank you, Doug. What are students for? So a significant percentage of my PhD students are using it on a regular basis. So hopefully I can persuade you to use it more frequently in this talk. I do want to acknowledge some of our most notable collaborators, including Doug, who is our regular user, who's worked with us on a number of aspects of it. I'll talk about in a little while. Lee Giles, who's here in the back, and Ji Tang. I don't know if he's here, but we've benefited from collaborating with a number of teams, and they've been very generous with both their software, their insights, and the data resources. So what are the unique capabilities of Semantic Scholar? Why should you use it? There's actually a lot of little things, but let me just mention three things. First one, related to this issue of cutting through the clutter, we have, as I'll show you in a second, facets that allow you to home in on results. So you may start with 3 million results on deep learning. With a small number of clicks, you can end up with 3 or 4 papers that you can analyze. We provide overviews of the papers via key phrases that are automatically generated. We identify the data sets used in the different papers, which again helps to guide your search. Another thing that we focus on is which citations and references are actually influential. So I mentioned you have this paper, it's been cited 1,000 times. You really can't afford to look through each of those more recent papers to find what's the relevant recent work. What we do is we analyze the citations automatically and decide which citing papers were really influenced by the current paper. I'll show an example of that. And that often results in a compression of a factor of 10 or 20 in the number of papers you have to examine. And then the last thing, the number of actual papers, any of us, even the most voracious reader, the number of papers we'll read in our lifetime is limited, right? And at the same time, the number of papers published is growing exponentially. So part of the idea of Semantic Scholar, part of our hypothesis is, can we avoid reading the paper completely? Can we home in on an appropriate sentence? Can we home in on a figure or a table so that we don't have to read the paper? And again, we provide mechanisms to do that, simply to enhance your efficiency as a researcher. So let's go to the demo, which requires me to see what I can do here. All right, so that went well. The demo is going really well, but you can't see it. Thank you. Okay, so this is what it looks like. Let's do the query I mentioned. Deep learning is one of our examples, and there's all kinds of little goodies here. For example, we note when papers are mentioned on Twitter and social media, and we throw those up on top. We also give you a little escape. So if you're not happy with what you see here, with one click, you can get to Google Scholar and look at what's now 3.66 million papers. So part of my argument to you is, why use Semantic Scholar? Because you can always easily escape to a more familiar ground if you need to. But more interestingly, okay, I've got these millions of papers. Let's say in deep learning, I really want to see Yoshua Bengio's work on deep neural networks. So with 2 clicks, I've gotten down to 4 papers, right? That's a much more manageable set. I can also, as I said, restrict by the data set used, the publication venue. And then when I look at the paper itself, I have a whole bunch of information about it. So we have these automatically extracted key phrases. We've extracted the figures and tables, so you can quickly cycle through and see the different figures. Remind yourself of something if you read it before. You can look at the results used. They're easy to share via social media. So a lot of helpful information. And then this paper is from 2009. So if I want to look at more recent work, I'll look at papers that cited it. And again, in our corpus, this paper has 852 citations. But we've been able to analyze this and identify 41 papers that were really strongly influenced by this paper. And if I want to see why this is ranked as the one most strongly influenced, I can look at these citation excerpts and see quickly what paper A is saying about paper B. So I'm just giving you the flavor of all the different things you can do here, and all of them are based on machine learning, machine vision techniques, etc., helping you guide your way through the paper. We also don't just have you look at the citations. You can click and look at the references. And again, out of the 206 references that this paper makes, we've identified 28 as ones that the paper really builds on. And again, we tell you why. So hopefully that gives you a flavor of part of why. Yeah, if you want to switch back. Thank you, Chris. Okay, why I'm excited about this engine. And another thing I'd mention is we're very responsive. You know the old line, Avis, we try harder. If you see something you don't like or something you want to improve, send me an email. We're constantly improving it. Over the last few months since it's been launched, our traffic has been growing nicely. I like the shape of the curve. It's still, of course, pretty small. In the last 5 months or so, a little bit more than 500,000 people have gone through the system, but the number is growing rapidly. Let me give you a quick peek under the hood. This is the work that Doug Downey and his student and I did together. We looked at this problem of, can you automatically identify key phrases that describe the article? If you have a controlled vocabulary, that's not too difficult. But if you don't, right, if the paper is on an arbitrary topic and you want to allow arbitrary phrases that describe it, it's a harder problem. Here's how we formalize it. You want to identify key phrases that best describe an article. And actually building on that, then you want to have a set of phrases that actually describe a set of papers, right? And those are the facets that I showed you on the left that allow you, for example, to pick DNN as a way to cut through all the deep learning papers. I won't go through all the details here. Obviously, we need to consider which phrases are relevant and informative. At the same time, their coverage, their redundancy. We formalize all these things in a integer linear program, and we've gotten some pretty good results. I want to mention also that the data set that we've created, unlike Google Scholar, is available to the research community for research purposes. Again, just send an email. It's on our FAQ, and we'd be happy to share our data with you. So here's an example of some of the fun topics we've addressed. We asked the question, can you predict citation rates in the future, right? We're all aware of kind of this endless fascination we have with citation rates, H indices, etc. This is joint work with Luca Ways in the UW Statistics Department. And make a long story short, we found out quite remarkably that we're able to develop learning models that are able to predict H indices 10 years into the future with less than 20% error on average. So here's an example. The green line at the bottom is our method. And likewise, we're also able to predict individual paper citation rates quite accurately, even 10 years into the future, which is a little bit scary. But again, just an example of a fun thing you can do with our data. Okay, so Chris showed me I have less than 5 minutes left. Where are we going? And I would summarize that quickly by saying we're trying to get more and more ambitious about what we can extract automatically from the different papers. For example, we're looking forward to being able to type in something like information extraction, the name of a subfield, and getting a very comprehensive overview that tells you, okay, here are the different tasks where this technique was used. Here are the different accuracies that were achieved on what data. And by the way, this is not something we can do today. So this is future work, and this is kind of a mock-up. Or maybe, and we want to be able to tie in the particular results we're describing to particular papers. So when we tell you a number, it's easy with one click to get the provenance of that. Likewise, if I type in a technique like Gibbs sampling, I can start to see the different tasks that this technique was used for. Maybe the size of the circles represents different areas and how heavily it was used in the different area. And so on and so on. And again, have an easy way to find provenance. Thinking even further ahead, we're going from this, and this may be a nice prelude to Häufungstag. We're moving from computer science to neuroscience to the biological sciences. And I always like to put up one of my favorite lines from Eric Horowitz, which is, he says, it's the absence of AI technologies that's already killing people through errors, specifically preventable medical errors, right? So one of the reasons that I'm excited about this project and the future capabilities is that doctors and medical researchers are using very primitive tools, whether it's PubMed, or I've even heard stories of people looking up doctors rather than just people looking up information in the emergency room through Google Scholar. Okay, that really does not make sense. We need more powerful technology for these people. Moshe Vardi said that we have a moral imperative to work on AI because we're going to be saving people's lives. So important thing to remember. And then last thing from the Semantic Scholar vision, and of course this is way beyond what we can do today, but it's exciting to think about, can we, using machine reading, analyze different papers and synthesize information across the different papers and actually generate hypotheses and potential experiments and go from search engines to AI-based discovery engines that maybe can help find answers to science's thorniest problems. Thank you very much.
Thanks very much, Warren. We have several minutes for questions and some mic runners in the back. think it's on. Can you?
We have several minutes for questions. The person in the back.
Well, thanks for the interesting talk. So one of the reasons I still go to Google Scholar is the coverage of all the other tools don't have. In contrast, what do you think is the best way to increase the coverage of the articles in the other data sets?
Crawl, baby, crawl. So let me answer a different question than the one you asked. Because, hey, I think that coverage is a little bit illusory, right? It's absolutely true that Google Scholar has this phenomenal coverage, right? And it feels good, right, to type in a query and see that there's millions of papers and thousands of citations. But how many of those papers do you actually end up looking at? I would argue that it's at least worth considering whether you're more effective with a tool that is admittedly less comprehensive, but gives you a stronger ability to navigate the paper space. I don't have the data or user study to prove that point, but at least it's worth thinking about.
Thank you. Just to follow up on that, so the different representatives of different of websites are here. Do you think that it's useful to get a coalition of sharing the data between these scholarly website and then have a open access repository that everybody can fetch from and build their value on that? Thank you.
That is such a great idea. I think we should have a workshop on this tomorrow. Sorry, just be thinking. So Alex Wade is organizing such a workshop headed in that direction. I do think that something along those lines would be fantastic, and more generally, allowing open access would go a long way. It is surprisingly challenging when you get to the details, but absolutely. I think that's a great idea, and I think other people do too. And other people that I mentioned, from Microsoft to sites here to RNetMiner, have shared data with us, and as I pointed out, our PDFs are completely freely available for research purposes. So we're starting to move in that direction.
So you mentioned ILP briefly. Could you comment a bit more on what kind of mathematical optimization problems you would like to solve? And I imagine even the problem you have listed here could be cast as some kind of an optimization problem. So can you comment a bit on how advances in optimization technology could help further this vision?
Well, what we find is that actually, both with balancing these different constraints on the key phrases, redundancy and coverage and informativeness, and actually a number of other problems that we've worked on at AI2, we have found ILP to be very helpful. But the hard part is modeling the problem in the constraint language. Once we've done that, and that's something that we iterate on successively, we just use commercial solvers. So I don't know if I'm addressing your question, but from our point of view, the problem is much less in optimization technology. Let's leave that to, I'm blocking on the name of the commercial solvers, but it's really hard to go from a domain to modeling it appropriately in the constraint language. That's something that is currently done manually, and it's surprisingly, I think, finicky is the word.
A couple of questions about the prediction thing that predicts citation and influence. What features are useful, and would you please consider not putting that online at the risk of having self-fulfilling prophecies?
Well, fair point. So we're not planning to put that online. That's a research enterprise. I should also mention that while our error rates are very good in aggregate, for any individual person who may be concerned, there can be quite a large error. So it's not a right. We're not attempting to reduce anyone to a number. The features that we used are kind of the obvious ones, including venue. The previous, right, it's a kind of time series, right? So the previous, rate of citations, and things like that. We've also played with all kinds of things like the number of authors, the length of the title. We've looked at a wide variety of features. I think it is interesting just to see, to play with this data, but we do have to be cautious about citation rates and how they're used in hiring and promotion decisions. Let me just end, because we're probably out of time, with one plug for in an imperfect world, which citation world definitely is, there's currently one choice, which is the number of citations, or it can be summarized by H-index, but it's based on the number of what we call raw citations. This is very, very noisy, easily manipulated by self-citations, right? All this has been documented. When we look at influential citations, it's far from a perfect measure, but I think it's quite a bit better than raw citations because, for example, we don't count self-citations. We don't count throwaway citations where somebody cites your paper in a long list of 10 other ones, right? We count citation as influential if, based on a machine reading of the text, it does seem that paper A influenced paper B. So I do think that this citation count world will be better one if we start adopting influential citations and potentially even improve on that metric as well. Thank you very much.
Thank you. You can leave it on if you want. All right. I think, did they move the clicker over? Pardon me just a moment while we switch to the appropriate PC. And all right. So, oh, great. So our next speaker is my colleague, Hoifang Poon. He's also a researcher in the natural language processing group. He received his PhD from the University of Washington under Pedro Domingos, and since joining our group, he's eagerly pursued this agenda in applying machine reading to cancer genomics and precision medicine. So please, Hoifang.
Okay. Thanks a lot. Thanks, Chris. And as you can see later in the talk, a lot of this is joint work with Chris and other colleagues. So I'm very happy to have my talk actually right after Oren's, who introduced machine reading, which he pioneered, and also he has the last line motivating the medicine. That's sort of the area that we are kind of focusing our application on. So as Oren mentioned, one of the key missions of machine reading is trying to recognize important entities and relations from text. So for example, given a piece of text from biomedical literature, you might want to extract key entities such as protein, processes, and so forth. And then more importantly, you want to understand the complex relations that are expressed in the text. So for example, protein can regulate other proteins, but in turn they can be controlled by some other protein in the context of some processes like cell suicides and so forth. There has been a tremendous progress in the past on machine reading. A lot of them have been focusing on newswire text and web. Oren pioneered a lot of the work in those domains. And there is a pretty powerful insight for this kind of domain where because a lot of the facts that you care about there is a lot of redundancy. For example, like a fact about a celebrity entity, often they have been mentioned a lot of time, and they can be leveraged to actually to aid the machine reading. So relatively simple method can actually go a really long way in this kind of domain. In contrast, in the domains such as like healthcare, in sort of more specialized domain, there is the characteristic is actually quite different. For example, in biomedicine, what you care about probably are sort of the cutting edge kind of finding, which by definition are not mentioned a lot of times. So there's a very little redundancy to leverage. But so this basically actually presents a lot of great opportunity to actually develop more sophisticated NLP methods. So one of the things that Oren mentioned in his talk is sort of like a common bottleneck for supervised machine learning paradigm is that you need a lot of sort of the training example in order to teach the machine to be able to learn how to extract automatically from the text. So sort of an overarching theme for our research is actually how do we overcome that bottleneck by leveraging this new paradigm called distance supervision. Essentially, it's trying to leverage the related structured data that is available, trying to get information from there. And I will showcase a few examples later on about how a bunch of those challenges that naturally stem from the precision medicine domain, but also potentially applicable to other high-value verticals. So building on all these advances, so this is sort of a sneak peek of what we have been done so far is centering around this so-called literum project, where we were able to extract a lot of orders of magnitude more knowledge compared to traditional methods. And more recently, we have been starting to expanding from the machine reading angle and trying to build up a clinical decision support, which on one hand input on the genomic data, and then on the other hand suggesting potential decision, helping decision making for clinician, and then keep continuously learning from experimental results. And some of our preliminary results shows that by incorporating this kind of knowledge from literum and other knowledge bases, we can potentially help building good models to predict cancer drug predictions. So I will start by kind of motivating this cancer precision medicine domain, and then go over the machine reading work, and then sort of talk a little bit about this more recent cancer work. So many of you have heard about this great, really exciting kind of disruption happening in the genomic world. So in 2001, when the Human Genome Project concluded, we spent billions of dollars to sequence essentially a couple genomes. Nowadays, we can actually sequence millions of genomes, and each of those genomes actually costs less than $1,000. And if you look at the trend, the current growth rate, which is the red line, it's actually substantially outperformed the Moore's law. And actually, within a decade, we will be able to actually sequence the whole planet, everybody. And it's not just DNA we can measure. We can also measure messenger RNA. We can measure methylation, histone modification, and even to a lesser degree the protein. And so they together actually give you a pretty good multi-model kind of measurement about the sort of the cellular software that govern our health and disease. Of course, the unfortunate fact is that this is basically at the machine code level, right? So unless you can translate them into some sort of actionable space like disease diagnosis and drug development, otherwise they will be of little value by themselves. So one of the area, obviously with a great value proposition, is the precision medicine. And so the dream here is that rather than focusing on developing those blockbusting drug that is applicable to a general population, let's try to find out what went wrong at the individual level, and then develop drugs that specifically target them. So cancer is a particular attractive sort of disease group for this kind of vision, because by the time the tumor is formed, it's completely governed by the genetic mutation accumulated in the tumor genome. And it is account for almost a quarter of the death in U.S. right now. And also as the population age, the people who will be inflicted will grow substantially. So here is sort of what success might look like, right? So so this unfortunate individual has this late stage melanoma that has already spread. And normally he wouldn't survive for very long. But by taking this drug that specifically target the tumor's mutation in the BRAF gene, the cancer almost miraculously melted away in less than 4 months. So this is exactly sort of the dream scenario we want to get at with precision medicine. Unfortunately, we are not quite done yet because cancer is has the help of natural selection, just like HIV, and eventually figure out a way to get by the drug, and then the cancer comes back. So in order to actually fully kind of materialize the potential of genomics and precision medicine, we're basically finding ourselves in sort of a kind of a disruptive moment where there are two bottlenecks that that are standing in the way. So one problem right now is that cancer is driven by this complex landscape with hundreds of, if not thousands of mutations in each tumor, and they sort of get involved in like all the 20,000 genes. So now in principle, we have the measurement for all those 20,000 genes, but the question is how do we find the one that are responsible for the particular tumor? So there is if you think about sort of all the knowledge that we have already understood about those 20,000 genes, nobody can memorize even a fraction of them. But more importantly, those kind of knowledge are not independent. They are actually intertwined with each other because genes regulate each other. And so there is an even bigger challenge. How do you integrate all this knowledge to do automated reasoning? So let me give you a concrete scenario to think about this problem. So nowadays, a major cancer hospital already is routinely sequencing cancer patients, sequencing their tumor, and then trying to make best decision how to treat the patient. And what they do to deal with this kind of information overload is that they put a bunch of specialists in the room trying to form this so-called molecular tumor board, and basically a bunch of specialists trying to kind of collectively sort of manually going to either PubMed, ask friends, and so forth to figure out how to make sense of those hundreds of mutations, what are the significant ones, and what can we do about them. So as you can imagine, this is very hard to scale. And for example, Memorial Sloan is actually going to sequence tens of thousands of tumors. But on the other hand, their board basically meet every week and can only review a few cases every week. So you're talking about a very big gap here. On one hand, we have this cutting-edge technology that can give us this measurement, but on the other hand, we cannot actually effectively use them. So what we really want is to actually be able to identify some of these repetitive processes in the decision-making process and then provide support to kind of improve their productivity. So one thing that the geneticists and the oncologists spend a lot of time on is like understanding how the genes interact with each other. So you can basically think of about it as a big gigantic knowledge graph, right? So the nodes are basically a gene and the gene products, and then the edge or hyper edges are basically how they relate to each other. For example, one gene can turn on another gene but inhibit yet another gene and so forth. So it's a very elaborate programming here. And if you look at all kinds of complex disease, cancer, diabetes, etc., they all stem from kind of perturbation of multiple genetic pathway. So here are the sort of the famous cancer hallmarks. So basically, each of them, you can think about it as sort of a specialized skill that cancer has to acquire. So cancer has to acquire all this kind of skill set in order to become a fatal one. So for example, they need to grow a lot of blood vessels. They need to replicate indefinitely. They need to kind of invade the tissue boundary, so to migrate and metastasize. So each of this kind of module actually can be perturbed in different ways. They break down to smaller modules and so forth, and the whole process goes recursive. So by the time when you get down to the gene level, and when you look at the statistic, they become so convoluted, and that's why it's very hard to just look at simple gene-based statistic and try to make sense of what are the driving mutations. Moreover, even if you figure out here is a driver pathway, and even if you figure out, okay, there is an effective drug that blocking this driver pathway, cancer is incredibly robust because of all those alternative pathways that can actually get invoked to compensate for the loss of the original pathway. So this is why cancer kind of, why relapse occur. So this sort of motivate the kind of the machine reading agenda of it is trying to extract a lot of those knowledge which has already been known, but they are just scattered in the millions of papers. So Oren talked about like in computer science, so we probably think there are lots of papers for us to kind of keep track on. Suffice to say that in biomed, they have a slightly bigger problem. So every minute I'm speaking here, there are 2 new papers added to this biomedical repository. And every year they add like 1 million new papers. So it's definitely impossible to try to kind of read them manually. What we really want is to actually automatically scan all those texts and then build up this kind of knowledge graph, and which can then be used for automatic reasoning. So what you want to do is convert those tags, as you've seen earlier, and extract all this complex relation among the entities. So one problem for doing this, and in general, like this could be my one single slide to tell you why NLP is hard. The problem is that people are so creative in figuring out different ways to say essentially the same thing. So here are basically a few ways to say the simple fact that TP53 can inhibit another gene called BCL2. So in a small corpus, like involving a couple dozen abstracts, if we sit down and look at the words that have been used to denote this kind of negative regulation event, you can already see an extremely long tail. So if you do it in a standard machine learning way, then the first step you have to do is to get a bunch of experts who know about the domain, and then start to annotate example like this. So you start from text, and then you specify, painstakingly specify, okay, here are where the entity sits, and here are where the relation sits, and how the argument structure, and so forth. So this is incredibly expensive. And now tomorrow, if you have a corpus like talking about like blood cancer and so forth, and tomorrow you decide I want to do it in the lung cancer and other places, then a lot of terminology will change, and a lot of the things may not be able to transfer. So the challenge here is, of course, is not just for this kind of machine reading domain. It's general for supervised learning in general, but this problem is particularly hard here because this kind of text is not easy to just send them to mechanical Turk for average lay people to annotate. Also, often you have seen this kind of complex regulation event. They involve complex semantic rather than a simple spam or not spam kind of annotation. So the question is, how can we kind of overcome this bottleneck? So an overarching kind of theme of our research have always been trying to see whether we can see some sort of kind of a freely available resource that are sort of related, and trying to co-opt them to give us a supervision signal. So let me give you a very simple idea using a sort of a simple scenario. So because of this pathway are very important, Nature basically mobilized the editor at one time to try to collaborate with NCI, the National Cancer Institute, and try to manually read papers and put them into database. This is an incredibly high quality database, but unfortunately the Nature editor gave out after a couple of years because the effort is just too much. But the database is freely available, and we can try to see if we can make use of them. So in the database alone, it will probably tell you, for example, each row, it will tell you a particular relation. Let's say the first row says that TP53 negatively regulate BCL2, as you saw earlier. So knowing this fact alone doesn't give us an annotated example per se, because it doesn't tell us where does this fact come from, where is the text, and how is it mentioned there. However, if we try to look at the vast amount of the text that we can get, the unlabeled text in the PubMed, and then we can start to notice that, okay, I already know there is a relation between BCL2 and TP53. And then there is a sentence where these two entities actually co-occur. So I can start to kind of speculate that maybe this sentence is talking about these relations. So I can start to kind of treat this as a potential training example that talking about this fact. And obviously, you don't stop there, right? You don't just using your existing knowledge base to annotate the sentence. What you actually do is to treat them as potential positive examples, and then you can use them to throw to your favorite machine learning algorithm to train up an extractor, and then you can now extract facts from new papers and extract new facts involving entities that are not even specified in the database. So this paradigm is known as distance supervision, and it has been sort of a very kind of a promising paradigm to get over this kind of annotation bottleneck. So we have successfully applied this to sort of do a PubMed-Scale extraction. So I told you earlier, the Nature editor, they basically spent 2 years to extract it, about 10,000 unique gene regulation events to put in those databases. By bootstrapping from that, we were able to scan the PubMed basically within a day. And we got millions of unique new regulations. And we have already found a bunch of applications, including a recent kind of breast cancer study that will be soon in submission for that. So far we talk about this distance supervision, and a lot of the existing work are focusing on the simple classification scenario, where you basically have an instance and you want to say, okay, is this a positive regulation, is this a negative regulation, or so forth. But in reality, you often have tags that actually tell you much more than that. Not only that there is a regulation event involving these two proteins, but also it tells you that this regulation is controlled by yet another proteins. So we basically developed the first approach that generalizes distance supervision from doing classification to actually be able to extract this kind of complex knowledge by automatically learning a semantic parser. So one of the encouraging initial results we got is that by doing this, we evaluate on a particular data set where you can also actually train up a supervised approach because it has fully labels. So we can actually compare head-to-head to a supervised approach. And of course, we are not, we don't aim at actually getting at the state-of-the-art supervised approach, but we were actually very competitive against like average supervised approach. And we are using much less information in the supervision there. And if you're curious, basically the gist of our approach is like we start from the knowledge base with some of the known facts, and we start with the unlabeled text and also the syntactic analysis like dependence tree. So essentially, we're basically imagining that the semantic annotation, the semantic parts that represent those complex knowledge is actually always out there. They are just like the latent annotation that you don't observe in your training data. But what we can do is that we can essentially model that as a hidden Markov model. So essentially, the Z is like the hidden, represent the hidden, the latent semantic state. And then you can start to model the emission probability, like coming from a semantic. If you are in this semantic state, you may be able to generate this word and this dependency, and then you have a transition probability going from one semantic state to the trial semantic state. And so one thing, obviously, you can do EM to recover the grammar and also the semantic parts. So one twist here is that how do we use the knowledge base? Essentially, what we do is to incorporate a Bayesian-like prior to score all different kinds of semantic parsers. So if they are compatible with the knowledge base, then the prior likes it a little bit better. So this is effectively the virtual evidence that first proposed by Julie Pro. So this is how we actually be able to learn the semantic parse without direct supervision. So far we talk about the extraction, and we're limited to explicitly stated facts, but often this entity have relation, like genes in the same family tend to have similar relation, and there are, if we know that gene A regulates gene B regulates gene C, then A probably regulates C, and so forth. So you can imagine encoded this up using like first order logic and probabilistic, and using something like Markov logic to do the reasoning, but the catch is that, so this kind of approach is very general, very powerful, but the catch is that the inference is sharply hard, it's very expensive. So more recently, we have also trying to explore another alternative direction, which is that we try to aim at a less powerful, less general kind of reasoning, but it can be done lightningly fast, basically a matrix operation. So essentially, we are trying to map each entity and relation to a vector. And then given that embedding, then you will get a score. You can score arbitrary relation candidates, triples. But so the key thing is that how does that embedding come by? And we are using a different kind of distance supervision here, trying to push up the score for the known relations and so forth. So there are some promising results. And more recently, we have been looking at a different type of knowledge that other than just a gene-gene interaction. We are actually trying to look at how about gene-drug interaction, for example. Depending on the mutation status on the ALK gene, a patient's tumor may be susceptible to crizotinib or not. So we want to kind of understand that, and there are explosive results. But because of the sequencing and so forth, there are a lot of new paper come out with the findings. But the state-of-the-art approach is basically some oncologists trying to review papers and then curate this knowledge base. And one of the popular sources is this GDKD, and it has about 160 unique interactions here. So suffice to say that we try to kind of tackle this approach. One of the challenge here is that we need to model actually the discourse because a lot of this knowledge actually, if you look at where they occur, the author may say that we try to start this drug, but then in the following sentence, it may say that if a person have this particular mutation, it may be responsive or not, without ever mentioning the drug again. So we actually need to expand our reading from a single sentence, which is predominantly what existing work have been focusing on, to actually cross-sentence. And so we developed the first approach that try to apply this general distance supervision to this kind of problem, and we get a couple of the magnitude increase. So we are putting all this knowledge in this Literum database, and which is on Azure, so it's available for both browsing and web services. So I will just quickly, in 1 minute, tell you a little bit about a use case in basically trying to use this knowledge to try prioritizing the drug combinations. So we are in collaboration with the Nye Cancer Institute for the BeatML project. So here's the problem, is that all this kind of relapse and recurrences, this basically motivated direction to try to think about not putting just a single drug, which may be very precise, maybe having very little side effect, but on the other hand, it's very easy for cancer to get around that. So instead, let's try to think about how about putting multiple drugs, and so to sort of preempt the cancer's escaping route. The challenge here is that we already have hundreds of cancer drugs, and even if you just think about pairwise combination, there were hundreds of thousands of them. And so the problem here is that how can you choose a subset? How can you help oncologists to pick a subset of a combo that are particularly promising, and then to do experiment with it? So in a nutshell, what our approach is doing is that we have a fair bit amount of how drug acting on a particular targets, but we are trying to augment that with the knowledge, the networks that come out from Literum. Because the key is to understand that when you target a particular gene, what is the ramification in the rest of the network? And that really determines the toxicity, the side effect, and also whether simple compensation pathway exists and so forth. So I will skip to sort of some of the kind of the highlights is that when we incorporate the Literum knowledge base, we were able to actually predict the efficacy of the drug in the single drug case, where we can get a pretty big improvement. So, so the next step right now we're working on with OHSU is trying to actually put that into practice with drug combinations. Amazingly, DARPA, actually, some of you might have heard yesterday that they actually have this program called Big Mechanism that actually have a lot of overlap with this vision, and we are part of a team that is led by Andrei Ryszewski, who is actually sitting right there. And so another thing, so far I've been talking about cancer. Just so before I wrap up, I just want to point out that there is sort of an even bigger kind of precision medicine agenda that incorporate all disease groups. For example, chronic disease, which currently costs more than 86% of our healthcare costs, and there is a lot of information in the electronic medical records that could be actually co-opted to use to actually improve, to tackle that problem. And there is actually almost a perfect parallel with the literature case. So here you often have lots of information that are spelled out in the clinical notes that are almost impossible to capture them in structured form a priori by doctors. So naturally you want some sort of machine reading to convert them to structured form, which can then be used as sort of a big time series. Then you can start to kind of predict sort of disease progression and so forth. And I just heard that Chris Ray have already done some exciting work in that space, so we might be able to actually hear some of that. So, so that's the end. So I want to thank all my collaborators. Obviously, without them, I cannot do any of this. Chris has been collaborating with me from day one on this agenda, and also Andre is a very close collaborator and so forth. So thank you.
We have time for a few brief questions between speakers.
So are there any public... Are there any publications about the DARPA big mechanism work where we can see about advances in machine reading and knowledge representation?
Yeah, that's a good question. So I can't comment on the overall program because it's still kind of relatively new. I think we have a few work. Some of this work that you have seen actually is basically within the scope of the program, and Andre and I also have some work that are in the pipeline. So that's a work that's sort of in our group. But I'm sure other kind of team, they also definitely have a bunch of work that is in the process.